right, good morning. How you guys doing? Doing okay? How did the MATLAB stuff go? Was it useful? Was it kind of not sure?
Seems a lot more useful than the first.
Okay,
Do you have the plotting stuff? It seems like some of the stuff I don't think you can write in Excel.
Yeah.
So I think it's useful.
some mixed opinions. Katie felt like maybe it wasn't so useful, or some of it was.
It's like a lot at once, so I feel like by the end of it, I kind of not as much as I would like.
Right, right. So the pace of doing like two segments like that without anything to do with them maybe is a little too much.
Maybe I think the way that I personally think, and I'm not great with memorization, so that might be it, but they kind of snowball it really fast.
Yeah. Do you feel like you at least have some grasp of like what could be done with it if you went back and figured it out? Okay, so that to me that's I think mostly what I'm after because I'm not going to test you on it. I'm not a MATLAB instructor. I've never I was thinking about it. I was like, my gosh, it's been a very long time since taken this. Took it my freshman year of college, and so I was thinking back on that and I was like, I bet I could go find those assignments. And I was thinking, and I bet it took me like 2 or 3 months before we got to some of these concepts because we were doing the very, starting from the basics. And so I was like, well, to show you guys this and what should I expect? Well, it's going to be very different than, as even than if we were just straight up having a MATLAB course, right? So at the moment, that is kind of my expectation is that you can kind of see what you could do and start learning a little bit about how to do. Um, so please continue giving me feedback about it as we go. I was looking through. There's the MATLAB's website had something to say like, well, we're going to retire this course set soon, but maybe try to do this other one instead, which is like building MATLAB fundamentals or something like that. But everything you've done so far is like in that same section. So we'll probably continue with that a bit. I think it might be helpful to go through a few more pieces. Okay. Another aspect for logistics was brought to my attention last time that I had placed the second exam right before Thanksgiving, and perhaps that might not be ideal because people might travel that day. And so, if you guys are okay with this, I'm going to move that one period prior. So there's still a couple. I cut off just a little bit at the end here. There's still a couple of classes after Thanksgiving before finals week. So instead of putting the exam on that Tuesday of Thanksgiving week, I propose I'll move it forward by one course period. So Thursday, the Thursday before Thanksgiving. I don't know if we'll keep this as redox chemistry. I'm not sure exactly how far we'll get or how quickly we'll go. But after that second exam, we'll basically be focused on making a MATLAB, Excel kind of analytics project possible. Might be adding a bit of other content as well alongside that. But any issues or concerns about moving it that way? Okay. So if you do, please bring that up to me. But for now, I'm going to have this as the plan. And I made some small updates according to kind of what we've done so far. Again, we're going to adapt a little bit as we go. Okay. And on that note, we will be today doing a quick follow-up on the proton balance stuff that we talked about, and then getting into kind of making a solution for a given solution that has an acid in it. So solutions for solutions. Okay, so a note, and this is from the other textbook I'm using a bit. the one that actually has problems. This says one thing we can do with the proton balance is we can essentially categorize it or describe a proton balance in another way. And that is that we could say we have total hydrogen, so tot H in solution, and we can make a comparison for the total H in solution given some arbitrary solution. We could say there's each pair we have an acid and a base. So water, for example, with H plus and OH minus. And for some generic acid, HA, we'd have A minus and of course H plus, right? So for any pairing, we could describe, okay, here's the conjugate acid, here's the conjugate base, all that. So we have to, in order to do this tot H evaluation, we describe all those pairings, and in a simple water solution with a monoprotic acid like HA, that's kind of what it would look like, and that's not a very good. These would be all the species involved. Okay, so for each grouping, for each pairing, we have to define some reference. It's arbitrary, but we ought to use whatever is probably dominant. So we're going to go through a quick example to explain what this is, how this goes with acetic acid. And then we'll stop and think about, okay, well, if we made that proton balance where we sum up all of the sources for H plus compared to all the sources for OH minus, we'll see we arrive at the same condition. So for this tot H evaluation, we take here, we're going to use water and acetic acid, so AC minus. And all of the species are described below, and we can then say how many H pluses are we adding for each particular reaction. So we have water, and we could say that we'd add 0 waters to end up with H2O. So 1 H2O is going to 1 H2O. Now, if we do this and say how many protons are we going to add in order to yield H plus, we get 1 here. So the prefixes here are what we're looking at. So we have 1 H2O with 1 H plus to get 1 H plus. So we're doing this for each species. So the H2O and the AC minus are the reference species that we selected, because water is dominant, and then the AC minus maybe we're guessing is going to be dominant here. So those are the two that we've chosen. So how many H pluses are we adding in order to get the other species here? All right, so we have 3 for H2O in order to get the H2O to get H plus and the OH minus. So we have to subtract 1 to get to OH minus, but we're adding 1 to get to H plus. For the AC minus, we have to add 1 to get to HAC. That's the acetic acid form. Or we take plus 0 to keep it at acetate. So it's just another way to describe either adding or subtracting H plus. And when we put these equations together and we take them at equilibrium, we can say that, well, this tot H at equilibrium should be the sum of the moles times, or excuse me, is that moles? It's probably not moles. I think that's the prefix. That would be the stoichiometric, like how many molecules per each, times the concentration for each X. So we could write that out explicitly. Here's the number of waters we had to add in the first case, plus H plus times 1. So we're just really taking each equation one by one and saying 0 for the first one, 1 for the second one, and so on. So we can carry this along for all those equations that we drew up and elaborate that, then simplify, because of course some of these will be going to 0, and we'll end up with a tote H equation that says H plus minus OH minus plus HAC, that's equal to our tote H added. So once we see that, that really gets us back to where we were starting with a proton balance. It's basically the same thing as using a proton balance, as long as we have this at equilibrium. So if we can say that about the equilibrium, and then we add some amount, some arbitrary amount of acetic acid, let's say 1 times 10 to the minus 2, so 10 millimolar of acetic acid, that's the input. The tote H input would be 1 times 10 to the minus 2. If we set that equal to the equilibrium, like we let it equilibrate, then we can say that 1 times 10 to the minus 2 is equal to that. And therefore, we can say, well, the amount of H plus we have is going to be equal to this stuff, because the essentially the amount of let's see, where did we go from that one? Yeah, because this guy is equal to this guy, right? So I'm really not good at drawing when I'm watching that screen. I have to watch this screen, so it's just like trying to write it as I was watching there. It was not working. Okay, so all of this was just to say there's another way we can arrive at the same proton balance with the tote H. So you might see this in some text or in some scenarios. I'm not too worried about mastering this one in particular. It's just another process we can go through to pair it up. Essentially, it's doing the same thing. So you'll see that at sometimes tote H, and ultimately we can come back to, well, if we added, 1 times 10 to the minus 2 moles per liter of HAC, we can put that here and do that. Okay. All right. I'm actually not even quite clear on the jump from here to here and how to explain that, so I'm going to leave it there for the moment. I'll probably try to clarify that next time, but again, I'm not too worried about this process. I'm not planning for us to use that a whole lot. If we do, we'll come back and make sure it's very clear. Okay. So what I am more interested in is for us to understand how do we use these equations and how do we pull these things together so that we can ultimately get a solution, meaning an equation that we can solve, right? A solved equation for H plus, or for that matter, for any of the particular components here. Give me 1 second, make sure. Okay. So when we have some aqueous solution with some acid in it or with some components, we're going to start with the simple acid again. And we want to find, maybe we know we've added some amount of acid, maybe we can measure something and we want to know pH, or we want to simply know what are the correspondences, what are the ratios. We need a governing equation that we can solve, right? Now, if we think about what's in what's in a solution of our water plus the simple acid, we have 4 species, right? We have H plus, we have OH minus, we have HA, and we have A minus. So these guys are all our species, and we're going to take it for a moment that they are all unknown. Okay? We have 4 things, and we want to figure out, we want to characterize the entire solution. So we have 4 unknowns. We're going to make an assumption that the activity of each is 1, so we can work with molar units and not think about that right now. There are ways to handle that. The book will talk about that. I don't know if we'll really get too far into that, but we can certainly do that for perhaps highly concentrated solutions or for salt, like highly saline conditions. Okay. From here, since we have 4 unknowns, we need 4 equations that relate these in a way where 4 independent equations so that we can solve a system of equations, combining, substituting, all that, in order to get our solution. So basically, I'm saying we need to use algebra. That is something that's we've done before. So we'll use, of course, the equilibrium equations that we know about. The Kw, right, defines the equilibrium for water, OH minus and H plus. We'll use the acid dissociation equilibrium. Ka is equal to H plus times A minus divided by HA. Then we can set up a mass balance equation to say the total acid, AT. And the book makes some comment that sometimes it's also referred to as C. But regardless, we're talking about the total amount of whatever acid that is in either HA form or A minus form. So that's a mass balance we can use. And then lastly, we have our electroneutrality equation. So these are 4 equations that are independent that we can use to find our solution. Okay, and as we move forward, one thing that we will find is helpful is, given that we are working with this mass balance equation here, the total amount is there, we can actually convert that in such a way where we can find a value of the proportion of a given species, right? So we can say, since we can say HA plus A minus is equal to A total, we can also say that essentially we can get some fraction of the total, saying, let's say HA divided by HA plus A minus would be equal to saying HA divided by the total. Of course, we'll put brackets. So it's kind of obvious, and I'm sorry I didn't write that very clearly here, but basically saying we can find a fraction of the total. We can rearrange this. We can use the fact that the total is HA plus A minus, and say we can describe then this alpha fraction. Alpha for some species I is going to be the fraction of that species in the solution. So the fraction of total. So we've probably seen this before, and we will see it a fair bit, where we have alpha 0 we can define as HA divided by HA plus A minus, and alpha 1 then we're going to describe that subscript using that to say that's how many protons have left the acid. That's the species we're describing. So alpha 1 is HA, or excuse me, alpha 0 is HA, alpha 1 is A minus. We could go on, and if we had something like phosphoric acid, we could go alpha 0, alpha 1, alpha 2, alpha 3, right? So we could say H3PO4, this is going to be in equilibrium with H plus and H2PO4 minus, which is then in equilibrium with HPO4 2 minus and PO4 3 minus. So we would end up, if we could solve an alpha 0 for that one, an alpha 1 here, alpha 2, and alpha 3. So we could do this for a rather complicated system if we wanted to. And as we will see, and I've already, I think, assigned you to do approximately that with the carbonic acid system, right? The carbonate system. And so I touched base with you already about MATLAB, about the learning assignment. Now the next thing you have is the assignment to make a little bit of code, right, for the carbonate system. Did I make that due Tuesday?
It's due on Thursday, but I
Thursday.
took a look at it yesterday and it just says follow instructions and no instructions.
If you click on the assignment, does it show you instructions there? Yeah.
There's a map.
Let me pull up Moodle real quick. I don't want to change my password right now. I just want to get to Moodle. Thank you. Sometimes what I see in the in setting up an assignment like that is different than what you might see, so you figure that out. Okay. Well, if I click it this way, this is probably what you see, which has no instructions, right? Okay. It's probably when you click submit, it might give you some, which is weird. So let me show you what I felt like I was being redundant if I put it there, because it's like description and then activity instructions. So you'll probably see it again when you click the submit button, but there you go. That should fix it. Just double check. Okay. All right. So given that you didn't even have a clue what the assignment was, let's talk about that for a second. What I tasked you to do was to write a script that plots each species of the carbonate system, so that would be the carbonic acid, bicarbonate, and carbonate, as a fraction of the total carbonate as a function of pH. So these are the alpha fractions. So the alpha fraction, so alpha 0, alpha 1, and alpha 2 is kind of that assignment. Okay? And plot that across pH. I'll give you some example today. I also tell you to note the equilibrium constants that you use. Probably have to look them up somewhere. Any assumptions that you make, and comment that within the code. And then upload the resulting plot you make, which feel free to make it fancy, now that you have some skills. And then also upload the .m script so I can take a look at that. And by the way, you're able to open the .m in Notepad, and if you really felt like it, you could copy it over to Notepad and upload a .txt, like a text file, would also be fine. But I think it'll let you just upload the .m, so I would say just go ahead and do that. Okay, so that's the assignment. I didn't really mean for you to be working on it before today, because I wanted you to do the learning assignments you did, and I wanted to cover what we're covering today anyway. So with that in mind, we'll come back to here for a moment and say that what we're talking about here is relatively simple. When we get to the carbonate system, we have to make it a little more complicated, but the same process holds true. The same alpha fraction setup is there. Okay. So, and for just to make very clear, for carbonic acid, we would call that alpha 0 because 0 protons have left it. And then HCO3 minus bicarbonate, we would call that alpha 1 because 1 proton has left it. And carbonate would be alpha 2 for that system. That's just the convention with the subscripts here. You could, of course, write out carbonate and put that in the subscript or whatever. Okay, so back to this. We recognize, like I said a minute ago, that we can describe the proportion of a given species compared to the total based on just writing it out very simply, like HA divided by the total, which is HA and A minus. Okay, and we can do that for each of them. So it'll be HA over HA plus A minus, or A minus over HA plus A minus, and so on. The other thing then, once we write that, we can say that to find HA, all we need is the total and the fraction that we calculated. That's just saying, with these alphas, it's like, okay, we have 20%, that's a ratio of 0.2 of the stuff is in HA. So if we know the total, we know to multiply that by 0.2, and then we get the concentration of HA. Right? It's very rudimentary when I stop and say it that way. But with all the strange nomenclature and things, I just want to make sure it's very clear. So we can get the concentration by multiplying the proportion that's there, that fraction, alpha fraction, times the total. So AT is the total, essentially the total A in whatever form, and that alpha fraction, of course, is the fraction of that. That also means that we can sum these two, alpha 1 and alpha 0 should sum to 1. And of course, in a larger system, we would say alpha 0 plus alpha 1 plus alpha 2 would sum to 1 also, right? If we had that many. So the total proportion is 1. Okay. Make sense? Yeah.
So does that mean that like H plus and OH minus are always neglected when you're making these?
Well, these are not considering H plus and OH minus, because this is just considering the amount of A. And A in this case could be acetic acid, it could be HCl, whatever acid or something that we're using, we're summing the acid, not the protons, right? So for example, this could be HOCl. Now, HOCl acts like an acid and dissociates to give you OCl minus. This is our free chlorine system. We're not bothering with H plus or OH minus. What we're doing is a mass balance in the OCl component. And so these fractions here are if we're talking about chlorine, we could say what fraction of the total chlorine is in the hypochlorous acid form, or what fraction is in the OCl minus form, the hypochlorite. So it's really just talking about the fraction one way or the other. So that's a good question to clarify. These are separate in that sense from the proton, because really these are derived from the mass balance equation on A. That's part of why it is independent of the water dissociation. Okay. So we can go from there and start pairing it with some other pieces. And this is something you've probably seen before. I know in one of the other classes I teach, I go through this solution, but I do it kind of quickly without much elaboration, and maybe I should provide those students a little more. But we can combine the Ka at this point with the alpha fraction to get the alpha fraction in terms of pH and the Ka value. And that's really convenient, because what we're doing is we're saying the ratio of one or the other depends on the pH and the equilibrium constant. That allows us to simplify the equations quite a lot, because then we can get rid of, even though we're talking directly about the species of acid, we can get rid of the proportion, the dependence of either species on, to find that, the dependence of either species on that. So we don't have to find HA concentration. It looks like we have to find HA concentration and A minus concentration, right? It looks very much like we need these two pieces of information to figure out what the alpha fraction is. But if we simplify this a little bit and say divide the top and the bottom by HA, and we can do that and that's not changing the equation at all. We end up with 1 over 1 plus A minus divided by HA. We could do the same thing on the other fraction, but dividing top and the bottom by A minus. And when we simplify that way, we get an expression that has 1 over 1 plus some ratio of A minus to A plus, or excuse me, A minus to HA. Likewise for the A1, the alpha 1, it's essentially the same, but we just have a reversed ratio there. So once we have a function here that says, all right, the proportion of the total that is, in the solution, the fraction of HA compared to total is equal to this equation. Now we can take from our equilibrium constant and substitute in here. And the way we'll see that is if we look at our equilibrium constant, Ka, the definition here has a ratio in it of A minus to HA. That's part of the definition. So all we have to do is reorder this a little bit. If we just simply divide both sides by H plus, then we have Ka over H plus equals A minus divided by HA. So then we take this guy and plug it in here. Of course, we can do the same thing if we flip it. We could say H plus divided by Ka is equal to HA, HA divided by A minus. And then we can put this one right here, right? So this is a way we can combine the mass balance set up here and add in a substitution using a different equation of knowns, right? Or a different equation that has some unknowns, but the different independent equation in order to simplify it down to the point where we are now, for either case, we have an equation that is a function of H plus and the equilibrium constant. And as we know from the way we started the semester, perhaps we can find that equilibrium constant based on either known quantities reported somewhere, or we could even just go and do a thermodynamic calculation. Okay, so that gives us a way, once we do the substitution, we end up with this equation or with this equation. Of course, we can also rewrite these a little differently to say that, to leave the H plus in there, and sometimes that might be convenient. But what we recognize is now we have an equation that is perhaps a little more useful given that there's fewer unknowns, right? Another thing we can say that I don't think I have written explicitly here anywhere, well, I guess we already saw this, right? So alpha 0 plus alpha 1 equals 1. That means we could say, if we know 1, let's say we know alpha 0, then we can solve alpha 1 by saying that's 1 minus alpha 0, which is going to be very obvious when we think of these as like fractions, right? The fraction of total, if 50% is the HA form, then the other 50% is going to be the A minus form. Duh, right? It's just saying that explicitly with math. So we can recognize we can use that if we had multiple fractions of course, the total, we could still do the same type of relationship. You know, A0 would equal 1 minus A1 plus A2, alpha 1 and alpha 2. Okay, does that make sense? All right, so from here, oh yeah, also mention we can do this with the diprotic and the triprotic systems. These will get a little more complicated because we'll have a third one here and there will be more dependencies here. Oftentimes we can simplify them, you know, for high pH or really low pH, maybe one of them goes close to 0, so we can leave that off an equation. But in general, this approach can get us there. Might take a little bit of elaboration. If you guys find that you just simply are getting too stuck on deriving this stuff for Thursday's assignment, let me know and we can pause that until we go deeper onto the carbonate system, which is coming soon. But I think it'll be good for you to go ahead and try and see if you can develop this for the carbonate system, and also to do that in MATLAB. Okay, so I want to show you what this would look like if we did put it in MATLAB. So I took the code from before, and I'll walk you through this in a minute, and run it. And mostly what I added is one little input. I adjusted the math a bit to do an equilibrium instead of on an HA system instead of on the OH minus and H plus system like we did before. So previously we did H plus and OH minus versus pH. And we did that according to KW equals H plus times OH minus. So of course this is rather simple. So now what I've done is I adjusted it so that we could get to use essentially H plus times A minus divided by HA is equal to Ka. So this was previous, and this would be the new. Okay, and I'll pull these up in MATLAB and talk about that. But one other thing I added, you'll see I have this input function, and I don't know if you've seen this in your learning assignments yet, but you can use in a script something that called input that asks the user a question in the command prompt, and then you type your input and it feeds that into the script. And then so what I've done here is I've set a variable Ka equal to 10 to the minus pKa, because the person will enter, oh, the pKa is 7.5. And then it's going to set the Ka accordingly, because we know, P of H is negative log of H or whatever. So the corresponding is to take 10 to the minus that, and you get your Ka value, right? So this is a way that I can let us input it, and then it says, all right, great, now here's the system. I made a couple other small updates, but we'll walk through that. Okay, so we are here. This is the, let me go ahead and load up, or actually just call the old one first. So previously I did this H versus OH, and there we go. And we could plot the raw concentration of H plus versus OH minus as a function of pH. And of course, we really only get high concentrations where we are getting close to pH 0 or 14. This is not a fractional plot, right? This is the raw concentration. And so we could do that, and we could also plot it on a log plot and see it that way. If we were doing a proportion, a alpha fraction for OH minus and H plus, it would look a bit different, but we can't really do a fraction that way for this system because we don't have that fraction of the total, right? Because water is essentially 1, and we're just not going to touch it in that regards. We don't treat water as fraction of the total like OH minus H plus. So we're not going to worry about that because that's just a little different case. So we've got that plot. So what I want to do is give it an H plus and an A minus. So H plus with A minus and HA, put all of that together into a plot. And so I basically revised that code, which is here, where for a pH range, we calculated the H concentrations as some vector, basically just a column, right? We made a column of values for the H plus and a column of values for the OH minus. And then we didn't even need this stuff. That was, didn't even use this. And we plotted that. Okay, so that was the first version. Now the update, I'm doing the AH and the A minus. So here I'm going to do an input. So when I call this one, I'm going to say AH versus A minus because that's what I named the script. And it clears the screen for me because I put in the clear. So these are the two commands. Clear clears the prompt window, and CLC clears all the variables that might have been there before. I might have had that backwards, but just little commands we sometimes ought to do to clear everything out and start fresh. So then it gets me to that prompt. It says, I tell it, I'm going to define Ka as the following, 10 to the minus, and then it demands a prompt. So this is, if we think about it logically, the script is running and it's saying, okay, clear CLC, Ka is equal to 10 to the minus. Oh, we need to ask for an input. So that's where we're at right now as I talk. So at that point, we can take, for example, an acid with a pKa of 3. So Ka would be 10 to the minus 3, and see what happens. What it's then going to do is, it was fussing at me, so I went ahead and created a column of zeros for the HA and the A concentrations. It's technically not necessary, but it says it's going to speed it up, and it was fussing at me, so I did it. So then, but everything else is basically the same, and then I'm going to put up the subplot, the two subplots, one with the alpha fractions as just raw there, and one with them on a log plot. Okay, so all the other stuff was happening the same. So I'm going to go ahead and enter that as pKa of 3, and of course it's popping up on my window. And what we'll see is these two graphs. So here, if we stop and think about it, of course I didn't elaborate in my code to label legends and things. I recommend you work on doing that because it'll look nice, and that's something that I probably ought to add, but I just haven't yet. But I think you've probably learned how to do that by now, right? Or at least know that you can. You might have to look it up. I know that I can, and I have to look it up, right? I'm kind of in the same boat there. I had to even look up the input. I was like, is it prompt? How do you do this? But I knew that I could, so I knew there was going to be a way to. All right. So on the top, what we see, and this is ranging from the value of 0 to 1. So that's the alpha fraction, and we know the stuff that's higher at the low pH, this is going to be the HA, right? Even without the legends, because we know that adding acid to the solution is going to push it more towards HA. So what we find is right at pH 3, these are going to be equal at 0.5. That's exactly what we should expect, right? Half of the solution is in HA, half of it's in A minus at our equilibrium point, or at our I mean, we can have an equilibrium point anywhere on this plot, right? But at that critical point, whatever the correct term is. And then, of course, the red dots to the right, these are going to be the A minus as it becomes more basic. If we plot that in a log form, we can see it's still sort of that bending shape and all of that. And the reason we might want to do this is just to recognize that this is becoming a very small fraction, right? We have 10 to the minus 10th. That's the fraction that is in the HA form up at pH 13 or 12 or somewhere around there, right? It's a very, very small fraction way over there, but we could still describe that as a fraction of the total. So this is possibly interesting to experiment with, because now we can say, well, let's check on chlorinate. That's typically the pKa is something like 10 to the minus, or the K is 10 to the minus 7.54, something like that. So we can plot that if we were curious and check it here, right? And of course, that equilibrium spot moved, that equal spot. Okay, so that's kind of the scheme, and what I've asked you to do is essentially create this for the carbonate system. So you don't have to have a prompt, because you can build in those Kas. You can do the prompt if you want to. You could make it in such a way where you could input some other constants. So you might experiment with that, but ultimately you ought to make it so that it's the carbonate system. And you'd have three plots here, right? You'd have the H2CO3, the HCO3 minus, and the CO3 2 minus. So that's kind of the essence of it. Now the math to get the fractions is going to be showing up right here in my code. And I don't think I needed a for loop here. And in fact, one of the assignments might have that I think you either did or might do next will tell you, like, hey, some people are inefficient and do a for loop when they could have done a vector, like a matrix multiplication, and that's me. So there's probably a better way to do it. But this is might be good to know at least how you can operate a for loop. I don't know. Perhaps I just need to go and relearn some MATLAB. At any rate, we get essentially columns, but we have to do that calculation given the fraction, right? So if we look at this, the way I wrote the math here, I said the AH concentration is going to be 1 divided by 1 plus Ka over 10 to the minus pH. That's basically saying over the H plus concentration, right? So if we stop for a moment and look back at our alpha fraction conversation, what I just wrote there was the fraction that is HA is 1 over 1 plus Ka over H plus. So that is exactly 1 over 1 plus Ka over H plus, right? So that's where I put that into my equation here, so that for every pH that I'm calculating, it went through that process. Okay, and my own homework is to do this without a for loop. Okay. So wanted to share that with you, show you what was going on, show you how we could possibly use MATLAB in that context. Does that make sense? Any questions? How do you feel about tackling the carbonate system? Not so sure. How do you feel about the MATLAB side of it? Feel like you can figure it out and make a plot? Or at least make a plot? Okay. Would it be easier in Excel for you? Yeah. It might be a good place to start. Start it in Excel, do it there, double check with yourself. And in fact, doing it in Excel would be, that's probably how I ought to start, to say, okay, how would I set this up to do this without a for loop? Right? And let me apply that same logical approach here. Okay. Speaking of Excel, I do plan, we'll continue on in a moment and get to an example that I'd like to work in Excel. I didn't quite have time to build the Excel file, but I can begin that with you guys after we explain the condition as a starting place. The book specifically notes for the next thing we're going to aim for, we can do it with Excel Solver or MATLAB. It's giving an example for Excel, and we're going to follow that, but it might also be something we or maybe just myself, I'm not sure, will explore in MATLAB. Okay, so moving on. That's what we just described is kind of that's an approach we can take to set up our system. Sometimes we might try to go a little bit further, perhaps with fewer assumptions, and really just get an equation that says h plus is equal to xyz, right? Or to have a function that gives us just one unknown as h plus. And this may be convenient if we have a very large and complicated system, and we want to solve for h plus, given that we know we added this much of this buffer, that much of that acid, and so on. Can we predict h plus or solve it? So it's another analytical challenge. And what we're going to find is we can derive an equation with one unknown and then apply some neat solving type, like a numerical solver type of solution, instead of a strictly analytical one like we were just doing. Okay, so we want to start with a linear initialization, like the most linear case we can start with. So it's convenient to start with the electroneutrality equation because there's no quotients. You know, the k has the fractions there. We don't want to do that right away. So we can start with the electroneutrality equation in trying to just find an equation with h plus. So that'll be in our continued example for some simple acid HA. We have h plus is equal to A minus plus OH minus. That's just the charge balance, right? So starting from there, we can recognize that, well, we talked from the mass balance that we can define HA as some function of this alpha fraction and the total amount of A. We can then rewrite this electroneutrality equation by plugging that in for right here. And then we have h plus is equal to the alpha fraction of times A total plus OH minus. And from here, oops, what did I do? I think I have this backwards. Sorry about that. Let me swap this so the order makes a little more sense. Okay. I just had my slides up backwards. So we swap this here. We get the substitute in the A minus here. We can rewrite it then, getting this in place. And then we can recognize we can change something for the OH minus from our water equation, right? So we're basically adding in the different pieces from our water equation, ultimately rearranging this function in terms of things that involve H plus. So essentially we're rewriting or reformatting or whatever trying to get all terms in relation to or in relevance to H plus with whatever else might be there. Okay, so then we have this, we have it here, the alpha fraction, OH minus. We can substitute in the KW divided by H plus. That's the direct substitution there. And of course, we also know that the alpha fraction can be defined this way. We talked about that already, which then goes to this function, Ka divided by H plus Ka. We also talked about it as 1 over H plus divided by Ka plus 1, right? That's the same thing. The book is keeping it a little bit less simplified so that the denominator is a little simpler. Simplified in a different manner, I suppose. So with all of that, we can see that we can have an equation here that is essentially equal to some amount of acid total times a function of H plus and Ka plus a function of Kw and H plus. So all of these pieces are coming together to say, all right, how can we get each component in the form of H plus and whatever else we need? Okay. So from there, we can set this equation to 0 once we get it to this point that we just got to. We can say, doing that again, we can say we'll set the left side equal to the right side, or that we already had, or we could subtract the right side from the left side and set that whole thing to 0, right? So take the right hand minus the left hand, or left hand rather, minus the right hand equals 0. Okay, so when we do that, now we can see essentially we've got one equation. It's got a couple things in there, the total acid and the equilibrium constants, but otherwise it's just a function of H plus and setting that all equal to 0. Now, it's not a very convenient algebraic equation, right? If I ask you to solve for the value of H plus here, what do you do? It might be a little bit of a headache, right? To do the algebra to get there. And so it's not a straightforward solution, and sometimes, you know, it almost looks like a polynomial kind of a condition. So what we can do is use a solver system to estimate. Now that we do have an equation with one unknown, assuming we know something about how much total acid we have in there. And the way to do this is to find the root value of H plus. And finding the root, you've probably seen this before in some other courses. But we're going to do this by making a guess. We'll guess at H plus, see how close the result here is to 0, and revise our guess and see if we're closer or further from 0. And we're going to keep doing that until we reach 0, and then we can go a little further, and we should then start departing from 0. Maybe we don't find the precise 0, but we can get very close, right? So that's the approach here. And ultimately, we're trying to minimize that function of the left-hand side of the equation minus the right-hand side of the equation. So really, this stuff. We're trying to minimize that. So there's a convenient solver in Excel that can do that. But let's describe just a little bit more specifically what we're doing. So we're going to take this function, f of a, the function of H plus, as equal to this component that we solved, and we're going to iterate that. And I'm sorry, I meant to just have it here. Okay, so the book is going to provide us a graph of what this will look like graphically, and I'm going to read a bit of the caption or the explanation here before we take a close look at the graph. So as we look for that root, we're essentially drawing this whole equation towards 0, right? So this we are moving towards 0. We're going to consider a case where we're given some AT, so some total amount of acid that's 0.1 micromolar or millimolar of that acid. We have a Ka given and a Kw we know. It's 1.01 times 10 to the minus 14. And so at this point, we can, with those values, we can test an H plus concentration, right? So if we put this in Excel and we set up that equation, we can say, well, let's give it a pH of 3 and see what happens. See how close that is to 0, that equation. And so we can check that. So that's what this is doing here, where we check some condition, let's say point A, we guess there, and we find that the answer for that function is 0.23 or something like that. And if we change it a little bit, then we would notice, okay, it's a little closer to 0. Now, if we started over here at point B and increased it a little bit, it's getting a little further away from 0 in the negative direction. Whereas if we bring it towards neutral a little bit, it'll be getting smaller. Now, one thing to notice is the way it's graphed here, we get kind of an asymptote there, where for a long time, for a lot of pH ranges, we're actually pretty close to 0 already. So that means that we get fairly precise, and that's the inset here, noticing that, well, if we get down to where we're at that 4th or 5th digit, then we're getting to a point where one little step we can notice, oh, when are we crossing 0? Now that might take a lot of computational power, especially if you are the author of this book who said that he did it by hand at some point with a calculator, did this method. Putting all that in. So to save your fingers with a calculator, or to save a few minutes with a solver, we might be okay with some error there, or not checking every 0.0000001 pH, because it might actually take a long time. So there's some consideration there for how accurate we need to be. But at some point we can minimize that function and get a pretty good crossing point for us. Okay, let's see. I think that's about all I needed to say from this. Yeah. Okay, does that make sense? And we can kind of see how when we set up that equation and we try something, we'll see where it goes. Okay. So following in line with that, these parameters were kind of that test case showing up in action. So when we put in these values, we also could recognize that OH minus should be, Kw divided by H plus. And given that we found some root there, we can then calculate the OH minus. We could then calculate the HA and the A minus. So we can calculate all of that given the 0 that we found, right? So that's how we solve the system. Once we have that value that we found, now we can describe, okay, that must mean this amount of HA is there, this amount of A minus is there, and so on. Okay. One thing to note is where we find that 0 value will change with a changing acidity constant, which temperature could change, for example, or maybe we just change the type of acid. And it's going to change with the amount of acid. So here we have the log C, or log total acid, versus the log Ka. So either one we change is going to change where that equilibrium point happens. So for a lot of these, we see 7. So if we have a very low amount of, low concentration of this, essentially the system is dominated by the water and the fact that water is neutral at pH 7. I think is kind of what the point is with that. But then inside the shaded regions, we can see where the acidity constant and things take over and change where, at what pH we find that minimization. So something that we can notice and be aware of there. Okay, so when we go to Excel, bunch of text here. I just want to highlight two things here that the book is emphasizing. There are two considerations we can make in order to make the whole Excel thing work out well. Because what we're going to do is use a solver to do those iterations over and over again and use them to find that very small change to the point where we're happy with it, finding a minimum. But as we saw, we might need a pretty small number here. If we are minimizing this, and we need to get it to that type of level of accuracy, one of the considerations is how do you do that in a way that's not going to bog down Excel too much? Likewise, how do we step across pH values appropriately? Really, we're stepping across H+ values. But if we stop and think about it, if we vary our H+ concentration from 14 orders of magnitude, that's a lot of H+ concentrations we need to check. So instead of doing that, it's going to suggest that we use different pH values. So we're not checking quite so many H+ concentrations because the pH scale is a log scale. Okay, so the two things then are, one, we kind of need to amplify that tiny number. So one is amplifying here. And specifically what we're talking about is this convergence criterion. That's going to say, at what point are we approximately at 0? Is this good enough? And it's just simply suggesting that we do that by multiplying our equation, left hand minus the right hand, by 1 million. Instead of digging down and telling Excel to go this fine, there might be some problems with that. Maybe MATLAB also. We just don't want it to stop too early, so we're just going to magnify that difference. Because if the solver was like, oh, this is 0.0001 difference, I think that's good enough. I think we're good. We're just going to magnify that difference is all we're saying. So multiply it by 1 million, and there we go. Okay, the other point is changing by pH instead of by H+. Because the pH scale here, that's 10 orders of magnitude, or 14 orders of magnitude, right? So okay, so that's the thing there, is we just know that we are scaling across a very large case, and it's going to be better to account for the fact that we're going through that log scale. Okay, so then the task that the book gives us, we'll just take a minute or two to think about it and look at it here. I think I'll pick up here next time. Maybe we'll pull up Excel for a moment now, and I can show you a little bit about Solver. But the task is to say, let's use this equation that we found, that's 5.17, and set up a spreadsheet so that Excel's solver function, which if you didn't know, we have to add that in as a tool, but it's available to anybody, you just have to add it. And then the solver will vary pH and check the equation and see how close to 0 we are. And so this is saying, set it up so that its solver varies pH and not H+ directly to find the root value of H+, and use that spreadsheet to find the pH and speciation at 25 Celsius in 1 atmosphere for a 10 to the minus 4 formula weight solution of HA with Ka equal to 10 to the minus 5. Okay, so a lot's going into that. It is giving us the equilibrium constant. It's giving us the amount of HA. This is A total. And yeah, so I think the 25 Celsius and 1 atmosphere is just saying we're standard state, so don't think too much about that. We're given the Ka, so we're not solving for that. We can perhaps assume that way that Kw is 1.01 times 10 to the minus 14. Okay, so with all that, I think it's just a matter of figuring out the solver, putting in the equation and then getting the solver. So this is what it will look like. We can set it up and do that. But I think it'll be helpful to do that kind of with you in Excel. So that's my plan. I didn't get quite that far, but I think timing-wise it works out just fine anyway. So that's the approach we'll take. There are some other ways you could maybe think about developing something like this and doing many columns, many rows, and checking that way, or perhaps plotting them. But I think this will be the most useful way. So we'll work on this one. We'll start here next time. I think that'll be good enough for today. Any questions or concerns? All right. See you on Tuesday.